All right, welcome back. This is section 2 from chapter 7, graphing exponential decay functions. This should not be too far off of what we just got done doing in with exponential growth functions. To begin with, you still, for exponential decay functions, you still have the same exponential function look. It's a, b to a certain variable exponent. Now, still, a has to be greater than 0. But this time, b, and this is what was in the words to review, has to be between 0 and 1. It can't be 0, because everything would be 0. It can't be 1, because then it would just always be a. So it has to be a decimal or a fraction between 0 and 1. The decay factor is why it's still part of this. The decay factor is that b value. So we'll say df. All right, this should look very familiar. It looks almost identical to this one from 7.1. But remember, b is now between 0 and 1. And the domain between 0 and 1. And the graph now goes down towards the asymptote. For a growth, it started at the asymptote and it went up. Here, it's going down towards the asymptote and barely touching. So for domain and range, domain is still all real numbers. So again, all real numbers for all exponentials. The range then is still the asymptote. So remember, the parent function is y equals a b to the x power. That's the parent function. But parents have their children, and y, the children function, the child function is a b to the x plus h plus k. Oh, actually, I'm sorry, not plus. This is x minus h. All right. So this x minus h part really doesn't matter too much to you right now. This is the key. This right here is the asymptote. Where it doesn't quite cross. So the asymptote for this equation here is a plus 0. So that means the domain is y is greater than 0. All right, so graph this function. Again, it's asking you, telling you probably to draw the parent function, but really what you're going to do is just go ahead and plot it into the y equals. Right? Put 0 in for x. That makes this -2. Put 1 in for x. So 0, -2 again, and then you have 1. If you look at your table of values, it's -1.5. And the plus k value is a plus 0. Therefore, the asymptote is y equals 0. It comes right through there. So let's plot the points. 0, -2. 1, 1.5. Here's the asymptote. You're going towards the asymptote in a decay. So it looks something like that. It's about as close as you're going to be able to get on that graph. So one thing you're going to want to remember, decays, they go towards the asymptote. I guess I should remove one of these s's over here. Huh? All right. Let's do another. This time we have some of these extra values. It says to begin this by sketching the graph, the parent graph. Don't worry about that. Okay. Don't worry about the translation. All right. What you're going to do is you're going to just plot it into the y equals. So you're going to put the equation into the y, and you're going to notice at 1, it's 3, At 2, it's 2.2. All right. You could also say at 0, it's 4.3. I mean, you could have as many points as you want if you wanted to have a very good graph. So let's plot those points. 1, 3, 2, 2.2, 0, 4.3. And you know that the asymptote is what is being added to the whole equation. So the asymptote is y equals 1. So here, let's use a different color. This right here is the imaginary asymptote. When I draw my graph, decays go towards the asymptote and never crosses it. Looks like that. So the graph asymptote is the line y equals 1. The domain, as usual, is all real numbers. And the range has to do with the asymptote. Look at the graph. Is it greater than the asymptote or less than the asymptote is the question. So the range, if it's y equals 1, that's y and then 1, and it's greater than. Now you can tell from this number whether the asymptote is greater than or less than. So you're going to want to add this to your notes here. If a is positive, the range is y greater than. If a is negative, then the range is y less than the asymptote. So put these in your notes as a reminder to help you for later. So let's keep moving here. Here's some checkpoints on your note-taking guides. All you need to do is plot a couple points. All right. Sketch it into your graph. Know that the asymptote is plus 0 here, so it's y equals 0. Here's your asymptote. Notice that it's negative, so it's going to be y less than 0 for the range, and the domain is all reals. So go ahead, plot this into the calculator. Put maybe a 0 in there, 0, -2. Maybe 1 or 2, whatever you want. Plot and then plot the points. So another point could be -1, -2.5. You could use 1 and 1 point, or -1.6. All right. So those are some of the points. 0, -2. -1, it's 2.5. 1 is 1.6. And basically, your graph then sketch would look something like that. It's going towards the asymptote. Checkpoint number 2. This, please remember, is the asymptote. So the asymptote is y equals -3. The range is y something -3. It's a. If a is positive, y is greater than. So we're going to have a graph that then is coming down towards the asymptote. Come up with a couple points. You might want to use the points -2, -2, 1.5. You could use 0, -1 if you wanted. All right, so let's take a look at that. So 0, -1, -2, 1.5. The asymptote is at -3. So your graph comes down through those points and never actually touches the asymptote. So let's do one of the more difficult. Oh, I guess they're all pretty much straightforward. Let's just do number 3, please. f of x equals 4 1/5 to the x. So please know this is a decay because this number here is between 0 and 1. The asymptote is a 0, so y equals 0 is the asymptote. Y is greater than 0 is the range, and domain, as always for exponentials, is all real numbers. So all we have to do now is graph. Let's take a look at finding two random points that you want to find. They can be whatever points you want. So I put it into the y equals form, and I found that at 0, it was 4, and at 1, it's 0.8. So plot those 2 points, 0, 4, 1, 0.8. The asymptote is right along here. So when I graph this, you're going to see it drops down and turns very sharply, and runs along the asymptote, never crossing the asymptote. So pause those whenever you need. All right, just like the exponential growth, exponential decay also has a formula. The growth formula had 1 plus r. You were adding the rate. This is subtracting the rate. So just like last time, a is equal to the initial amount r is a rate, t is equals a time. You have to be careful to know how these are related. Meaning if the rate is a per year rate, then your time has to be year. So using this information, let's set this up. A new television costs $1,200. The value of the television decreases 21% each year. Write a decay model giving the television's value after t years. Estimate the value after 2 years. Graph the model and do some more estimating. We now know the initial amount. How much was it worth? We know the rate. So just having those two pieces of information, you can write the whole equation. Y equals the initial cost, 1 minus the rate as a decimal. So rate, remember, is as a decimal, to the t power. 1 minus 0.21 is 0.79. So here's your equation. Write an exponential equation. That's done. We've written the exponential equation. Estimate the value after 2 years. 2 years is time, percent per each year. So those are related. So now simply put a 2 in for the equation. 1200, 0.79 to the second power. All right, you're going to plug that into your calculator and find out that after only 2 years, the thing has gone from $1,200 to $748.92. That is a huge depreciation. Now the next question, it says so we have now estimated that amount. Graph the model. Well, we know you're adding 0, so we know the asymptote follows this line. We know a point, 2, 748. We also know the initial value, 0, is 1,200. Now, if you don't know where I came up with these numbers, just put it into the y equals equation on your calculator and look at the table. So, 0, 1,200, 2, 748, and the asymptote down here. So you have your graph will kind of slowly start to curve out like that. Now, that makes sense because If an asymptote of 0 makes sense because at no point will the TV be worth nothing. I mean, you could take it apart and sell something, a piece of metal for a couple cents. So rework example 3. So we're reworking this television example with it decreasing by 12%. So your initial. So pause this and try it yourself if you want. 1,200 times 1 minus the rate to the t power. So the equation is, so there you go. This is the new equation. That means it goes through the initial point, 0 and 1,200. If you put t in if you put 2 in there, you'll get a new value at 2 that ends up being about $29. So now we've got 0, 929. No, not 0, I'm sorry. 2, 929. All right. The asymptote's still 0. Your graph looks about like this. The question that we forgot to answer from the others was estimate the number of, or the value, use the graph to estimate when the value of the television will be $300. So you'd look here and say, when does it cross? It crosses right about here. So after about 4 years, it will be $0. Now, our graph isn't perfect, so your estimation is an estimation. Looking up here, when will it be $300? It'll be $300 at about 6 years, we'll say. Now, I don't think those are probably the right answers, but that is a good estimation. All right, we're going to do one of each of these, the guided practices. Let's graph number 5, or number 6. So number 6 is that you have y equals -3 3/4. The x minus 5 plus 4. Okay, so the question is going to say graph the function, state the domain and the range. So domain and the range. Well, domain you should get that right all the time for these because it's always going to be all real numbers. The range is either y greater than the asymptote or less than the asymptote. Rewind and look back at your notes and you'll know that since this is negative, it's going to be less than the asymptote. And the asymptote is at y equals this number right here. So the range is y is less than 4. That should be actually the easiest part of these problems, is finding the domain and the range. And I'm sorry this is crooked, but you're understand that it shouldn't be. So here is a graph, a table. You need to have 2 points. You need to understand that we said the asymptote is here at y equals 4. So there's an asymptote. If you put, let's put some numbers. Let's graph using your calculator. So put it into the equation, the y equals equation, and look at the table. When you do that, you should see some things like if you put 4 in, it's at 0. So 4 is 0. We're going to find some nicer ones to graph. And maybe 5, 1. Nice ones. So 4, 0. 5, 1 is about right here. You're going to have if you looked at the graph, you could sketch the graph then and see that it cuts through and angles like that. So That is how this is set up. Let's look at number 8 or 7. Hopefully, all right, we'll look at number 8. I'm just going to write some of the information down for you. It says it's decreasing 7% each year. After 3 years, the new value is $3,000. So basically, when it's old, after 3 years, it's $3,000. It's now asking you to come up with the initial cost. So y equals the initial cost times 1 minus the rate to the t power. So let's look at this. We know that it costs $3,000. We don't know what it originally cost. We do know you're subtracting 7% per year, and that we wanted to do it for 3 years. So, all right, so now when you do the subtraction, it's actually 0.93 to the third power. And now when you divide by 0.93 to the third power, you end up with your original amount. So 3,000 divided by 0.93 to the power of 3 tells you that this, whatever it is, I don't even remember, snowmobile costs $3,729.69. That's how much it cost brand new. So that should be able to get you through all the practice problems. We'll work on them in class, but this should give you a good understanding of it.